Welcome to Generative AI Futures, brought to you by ByteGoose AI. Today, we are undertaking a massive and I think a genuinely fascinating deep dive into a paper that really represents a pivotal moment in computer vision architecture.
It really does.
It's called ConvNeXt V2, Co-Designing and Scaling ConvNets with Masked AutoEncoders. And for the longest time, the whole narrative has been that transformers, they killed the convolutional neural network. The ConvNet was a thing of the past.
That was the story, yeah.
This paper isn't just a rebuttal to that. It feels more like a complete systematic overhaul designed to prove that the fundamental principles of pure convents still hold.
They absolutely do. But only if you modernize their entire training stack. You can't just take the old model and hope for the best.
So the core mission of this deep dive, then, is to really unpack how these researchers successfully married the power of convnets, which are, inherently good at hierarchical feature extraction.
Right, that's their bread and butter.
With the scaling and efficiency benefits of modern self-supervised learning, and specifically the masked autoencoder, or MAE, paradigm.
That's absolutely right. And to really get it, you have to set the stage a little. Think about the landscape of visual recognition. It's always relied on three really interconnected factors.
Okay, what are they?
You've got the network architecture, so the actual design of the model. Then you have the training method, how you teach it, and of course the data, the volume of data you feed it.
And convnets, the best example being the original ConvNeXt V1, they were the undisputed champions of supervised learning. They absolutely dominated when you could give them meticulously labeled data sets like ImageNet.
But the moment the field pivoted, the second we moved towards self-supervised learning training models without explicit human labels, the vision transformer, or VIT, just took over.
It was built for it.
It was. VIT's architecture, which is all about processing sequences of image patches, was just perfectly suited for MAE's masking strategy.
And that's where the problem started for the old guard. The researchers in this paper found that simply trying to retrofit that excellent ConvNeXt V1 architecture into the MAE framework, it just didn't work.
It led to strikingly suboptimal performance, and that's putting it mildly.
That failure, that fundamental incompatibility, that's really the starting gun for this entire project, isn't it?
It is. It signaled they couldn't just drop in a new engine. They needed to completely rethink the chassis.
Which brings us to the core theme of the paper.
Co-design.
Precisely. The solution they developed is a testament to the power of co-design. They delivered this two-part solution that addresses both the learning method and the architecture at the same time. You can't fix one without the other.
Okay, so part one is a new training framework, one built from the ground up specifically for convolutions. They call it the Fully Convolutional Masked AutoEncoder, or FCMAE.
And that solves the really thorny challenge of how to handle sparse masked input in a naturally dense convolutional setting. And the second part is this ingenious, actually very small architectural fix. It's called the Global Response Normalization layer, or GRN.
And that little piece of engineering was designed specifically to combat this really destructive phenomenon they observed called feature collapse, which convents suffered from when they were forced to learn from these highly masked images.
And the immediate result, which I think is the perfect hook for this deep dive, is just the staggering scalability they achieved.
It's incredible. They created an entire family of models, 8 different architectures.
8 of them.
Yeah.
And they range from the super efficient Atto model. It's only got, 3.7 million parameters?
Well, tiny. And it still gets 76.7% accuracy.
All the way up to this colossal 650 million parameter huge model. And that huge model using only publicly available data.
Which is a key point.
It achieved a new state-of-the-art top 1 accuracy of 88.9%. This is ConvNet's not just surviving, but actually thriving in the modern foundation model era.
It's the ultimate vindication for the architecture. It proves that when you do it right, when you co-design everything, convolutions can be just as effective and just as scalable as transformers, even on what was supposed to be their home turf.
Okay, let's unpack that initial conflict a bit more. Section 1. ConvNeXt V1 meets the masked autoencoder. This shift to self-supervised learning, SSL, that's the massive underlying current here.
It is. It was driven by the simple, unavoidable realization that we can't manually label data fast enough to keep up with model growth. It's just not feasible.
We saw this start in NLP, right? With models like BERT learning by predicting masked words.
Exactly. And when that idea was brought into vision, MAE does pretty much the same thing. It masks out huge chunks of an image, maybe 60% or even more, and then it forces the network to learn future representations that are robust enough to accurately reconstruct those missing pixels.
And that pretext task, that game of filling in the blanks, it creates these incredibly powerful and transferable general-purpose features.
It worked beautifully for transformers like VIT, but like you said, when they tried to combine the tried-and-true ConvNeXt V1 with the MAE method, there was an immediate, critical architectural mismatch. So let's talk about why. Why were transformers so biased toward this method?
Well, it really comes down to how they see the world, how they handle the input.
Right.
A transformer treats an image as a sequence of discrete patches. It breaks it up into a list. And that simple act allows for what we call sparse processing.
So if the input is, say, 60% masked, the really compute-heavy part, the encoder could just skip the masked tokens. It doesn't even see them.
You only feed the visible 40% of the patches into the network.
Which is the definition of efficiency. You're getting a 60% reduction in your pre-training cost right off the bat without sacrificing the quality of the features you learn. It's a huge win.
A massive win. But a standard ConvNet is, well, it's fundamentally built on the principle of dense processing. It uses these sliding windows.
A V1 ConvNet operates by convolving filters across the entire 2D grid of the feature map, every single pixel.
So if you feed it a masked image, it doesn't know how to skip. It still performs the convolution across all those masked out regions. It can't just ignore them easily, while also preserving that 2D spatial structure that, defines what a convolution is in the first place.
So ConvNeXt V1 instantly lost the single biggest benefit of MAE, that computational sparsity. It was forced to process a huge amount of zero-valued or just totally irrelevant masked data.
And that inefficiency alone makes the pairing suboptimal from the get-go.
And it gets worse. There's a deeper learning challenge there, too. Standard ConvNets excel by leveraging local context. They rely on neighboring pixels to aggregate features. It's how they build up understanding from edges to shapes to objects.
But MAE aggressively masks out those neighbors. You're taking away its main tool.
You're stressing the system. And some previous research had already hinted that training ConvNets with this kind of mask-based SSL was really difficult because they have fundamentally different feature learning behaviors than transformers.
Right, because a transformer can look globally across all the visible tokens at once without that strict reliance on immediate spatial neighbors.
Which is perfect for a heavily masked image. This brings us back to that co-design philosophy. The researchers realized they needed to respect the 2D nature of convolutions. They couldn't throw that away, but they had to find a way to efficiently handle the sparse input.
You can't just adopt an MAE designed for a transformer. You have to propose a framework that is fully convolutional and sparse-aware. And then you might even have to modify the architecture itself to manage the stresses of that new sparse learning environment.
Exactly. So the big takeaway from this first part is that architectural integrity really, really matters. V1 was the perfect supervised athlete. It was a champion in its sport.
But it needed a completely new, specialized training regimen and, frankly, new equipment, the FCMAE framework and the GRN layer, to even be able to compete in this new self-supervised sport.
Okay, let's dive into section 2. This is the first major pillar of their solution, the Fully Convolutional Masked AutoEncoder, or FCMAE. The whole challenge was, how do you make MAE sparse and efficient while keeping that core ConvNet structure intact?
So the first step was just establishing the masking strategy itself.
Right. They chose a pretty high random masking ratio of 0.6. So 60% of the image is just removed.
And that's not an arbitrary number. That high ratio is actually crucial, isn't it?
It's everything. It forces the encoder to learn incredibly robust, non-local representations. It has to, because it can't just cheat by filling in the blanks from nearby context. Most of the nearby context is gone.
So it's forced to understand the global structure of the image, the overall scene, to have any chance of reconstructing the missing information.
Exactly. It has to learn cats, not just fur next to fur.
And since ConvNeXt V2 is a hierarchical model, with features getting downsampled in stages, how did they apply that mask consistently across the different scales?
That's a good question. They generated the mask in the last hierarchical stage of the network, which has the coarsest resolution. And then they recursively upsampled that same mask all the way back to the finest, highest resolution input.
Ah, so that ensures the 60% removal is consistent and meaningful across all the different feature levels.
Precisely. And they also did something else important. They kept data augmentation deliberately minimal. It was basically just random resized cropping.
Yeah.
They wanted to focus the model's entire learning signal purely on the task of accurate reconstruction. No extra noise.
Okay, now let's get into the real technical crux here, the sparse encoder design. This is where they solved that efficiency problem that completely sunk the attempts with ConvNeXt V1. How do you stop a connet from cheating by copying information from masked areas, and how do you get that crucial sparsity benefit?
This is where they get really clever. They looked outside traditional vision.
Where do they look?
They took inspiration from the world of 3D vision, specifically from large-scale point cloud processing.
Okay, that's interesting. Why point clouds?
Because in 3D, you're often dealing with scattered, non-grid-like data points. The data is inherently sparse. It's not a neat, dense grid like an image.
So they took that idea, and they treated the masked 2D image not as a grid with 60% of its values zeroed out,
but as a genuine 2D, sparse array of visible pixels, just like a point cloud projected onto a 2D plane.
That mental shift is the key.
It is. And the innovation that followed from that was to replace the standard, dense convolution layers in the encoder with submanifold, sparse convolution layers, but only during the pre-training phase.
Okay, what is submanifold sparse convolution?
It's a specialized operation that's designed from the ground up to work on sparse data structures. It only performs computations at the locations of visible, active input points. It effectively and efficiently ignores the 60% of masked regions.
So that's the silver bullet for the efficiency problem.
It is.
By adopting this technique, ConvNeXt V2 finally regains that huge computational benefit that transformers always enjoyed under MAE. It gets to maintain its convolutional heritage while achieving true sparsity.
And here's the key practical insight, especially for anyone thinking about industry deployment. These special sparse convolution layers, they are only used during the computationally extensive pre-training stage.
Ah, okay. So what happens after pre-training?
Once pre-training is done, the layers are converted back into standard, dense convolution layers for the fine-tuning and deployment stages.
Now, why is that conversion step so important? I mean, if sparse convolution is more efficient, why not just keep it?
Because of infrastructure and generality. Standard dense ConvNeXts are incredibly highly optimized on virtually every modern accelerator you can think of. GPUs, TPUs, specialized hardware.
Right, the whole ecosystem is built around them.
Exactly. Sparse convolution, on the other hand, often requires specialized, sometimes bespoke software libraries. That can really complicate deployment, fine-tuning, and inferences.
So by converting back to dense, the final model you ship is simple, fast, and portable. You don't need any special handling or software stacks post-pre-training. It's just a regular convet.
That's the beauty of it. And they even mention an alternative for certain hardware, like TPUs, where sparse convolution might not be natively optimized. You can actually simulate the sparse encoding just by using simple binary masking operations before and after a normal dense convolution.
That really shows they were thinking about implementation practicality from day one.
Absolutely. Now let's move to the other half of the autoencoder. The decoder. They chose a very asymmetric design.
A heavy encoder where all the core feature learning happens.
And an extremely lightweight decoder. It was composed of just a single plain ConvNeXt block with a dimension fix of 512. Super simple.
Why the big emphasis on lightweight? Why not a more powerful decoder?
Efficiency. Pure and simple. They ran extensive ablation studies on this. They compared their simple decoder against much more complex options, including things like hierarchical U-Net decoders and even transformer decoders.
And what did they find?
The simple single-block decoder achieved identical fine-tuning accuracy to all the complex designs.
No way.
Identical. But crucially, it yielded a massive 1.7x speedup in the pre-training time compared to the U-Net decoder baseline.
Wow. So the lesson there is that in this MAE framework, the entire burden of learning high-quality general features really falls on the encoder.
100%. The decoder's job is just a necessary auxiliary task. It's just for reconstruction. It doesn't need architectural complexity to succeed, and adding it just wastes time and energy.
So they're funneling all the complexity and all the computation exactly where it counts, learning strong representations in the encoder.
Exactly. And finally, the loss function was just standard mean squared error, MSE. It's computed between the reconstructed output and the target image, but, and this is important, applied strictly only to the mask patches following the original MAE protocol.
Okay, so they've built this elegant and efficient FCMAE framework. But despite all that, when they actually tested the original ConvNeXt V1 within this new framework, they hit a major snag.
They did. A really fundamental limitation of the V1 architecture was exposed. Severe feature collapse.
Feature collapse. This is the second great problem the paper had to solve. And it's what necessitated the architectural change we're about to get into. For anyone less familiar, can you break down what feature collapse actually looks like inside a deep network?
It's essentially a crisis of redundancy. Think about it.
Uh-huh.
If the network is forced to learn strong features from this highly fragmented, sparse input, which MAE does,
Hmm.
and it doesn't have the explicit guidance of classification labels.
Right. There's no teacher telling it, this is a cat.
Exactly. So it tends to find the path of least resistance. And that path, very often, involves multiple channels, or feature maps, learning the exact same redundant information.
Qualitatively, they actually visualized this, didn't they? They looked at the feature activations of the V1 model trained with FCMAE.
And they saw a host of dead or saturated feature maps. You'd have these channels that were either always off or always on or doing the exact same thing as the channel next to it. And this was happening primarily deep within the dimension expansion MLP layers of the convex block.
So if Channel 5 is learning exactly what Channel 6 is learning, you've just wasted a huge amount of computational capacity.
And, more importantly, you lack the feature diversity that's absolutely crucial for transfer learning to other tasks outside of ImageNet.
So to move beyond just looking at pictures of activations, they needed some quantitative proof.
Yes, and for that, they introduced the feature cosine distance metric. It sounds complicated, but the idea is pretty simple. Think of every channel's feature map in a given layer as a single high-dimensional vector.
Okay.
They just calculated the average pairwise cosine distance between all of these channel vectors.
And a high cosine distance means the vectors are pointing in very different directions in that high-dimensional space.
Diverse features.
And a low distance means they're highly correlated. They're pointing in almost the same direction.
Redundancy, or collapse.
Right. So what happened when they plotted this metric across the depth of the different networks?
Okay, so the supervised ConvNeXt V1 model, the baseline, it maintained good diversity until the very deep layers, which makes sense. The final classification loss kind of forces some redundancy related to specific class features.
And the MAE pre-trained VIT model, which was their gold standard.
It maintained high diversity throughout the entire network, a really healthy, diverse feature space.
But the ConvNeXt V1 trained with their new FCMAE framework.
It was a disaster. There was a clear, dramatic tendency towards feature collapse across most of the layers. It simply could not maintain the diverse feature representations required for effective self-supervised pre-training, especially when it was forced to operate on that sparse input.
So the ComNet structure, when it was left to its own devices under MAE, was just too susceptible to this internal redundancy.
Exactly. The sparse convolution fixed the efficiency problem, but it didn't fix the learning problem. This feature collapse analysis is what demanded the architectural co-design.
And this is where the Global Response Normalization, or GRN layer, finally steps in.
And the inspiration for it's just fantastic. It comes from biology.
Lateral inhibition.
Lateral inhibition, a mechanism found all over biological nervous systems, like in the human retina. The idea is simple. When one neuron is strongly activated by a stimulus, it actively suppresses the response of its neighboring neurons.
It's a sharpening process. It enhances contrast and increases selectivity.
And it ensures a much more diverse response profile across the entire population of cells. GRN tries to mimic that concept directly inside the deep network by enhancing inter-channel feature competition.
It literally makes the channels compete to be unique.
That's the goal. Let's walk through its 3 simple mathematical steps. You start with the input feature X, which is just a tensor containing all the channels for a given layer.
Okay, so step 1, global feature aggregation. We need some way to measure the excitement or the energy of each channel across its entire spatial map.
Right. And they found that standard global average pooling, which is what a lot of normalization layers use, actually performed pretty poorly here.
Why is that?
Instead, they opted for the L2 norm. The L2 norm is essentially the square root of the sum of the squares of all the values in that channel's feature map. It captures the overall magnitude or energy of that channel's response much better.
So it's a more robust measure of overall response strength than just a simple average.
Yes, an average can be diluted by a lot of zeros, whereas L2 norm really captures the peaks. So this gives us a vector G, where each element is the L2 norm aggregated statistic of one channel.
Okay, that makes sense. So step 2 is the competitive step, feature normalization.
This is where the magic happens. This is the lateral inhibition, and it happens via divisive normalization. For any given channel, let's call it channel I, its aggregated L2 norm value is divided by the sum of all the L2 norm values across all channels in that layer.
Huh. So it creates a relative competition. A channel's importance is now judged only against its peers in the same layer.
Exactly. If channel I has a really high response, it significantly reduces the relative normalization score of every other channel.
So if the network starts to get lazy and learn redundant features, say in channels 5 and 6, their high correlated activity will actually suppress the scores of other more unique features.
Which forces the network, through backpropagation, to diversify its features to maximize the overall output signal. It's an explicit mechanism to enforce diversity.
And step 3 is feature calibration.
Super simple. The original input responses, X, are just scaled by this new normalization vector. It selectively amplifies the highly competitive unique channels and suppresses the redundant ones that didn't earn a high relative score.
And despite this really sophisticated biological mechanism, the core GRN unit is mathematically simple. It has no learnable parameters initially, right? But they added something for stability.
Yes, this is a critical detail for optimization. They added a residual connection and two learnable affine parameters, gamma and beta.
And the key is how they're initialized.
The residual connection and the initialization of gamma and beta to 0 are absolutely critical stability tricks. Setting them to 0 means the GRN layer starts as an identity function. It literally does nothing at first.
So it lets the network start learning without this aggressive normalization, and then it gradually kicks in.
It only starts to enforce normalization as the training progresses, which prevents initial training instability. And because GRN now manages the feature diversity so effectively, the layer scale component, which was a stability feature introduced in ConvNeXt V1, became completely redundant.
So they just removed it in V2.
Gone. So they achieved this profound architectural improvement that solves the MAE-induced feature collapse without increasing parameter overhead or adding significant computational cost. They just replaced one stabilization method, layer scale, with a far more effective feature diversity mechanism, GRN.
It's just elegant engineering.
It is. And the ablations confirm it was absolutely necessary. V2, combined with FCMAE, hit 84.6% accuracy. This significantly outperformed V1 trained with supervision, which was at 83.8%, and also V1 plus FCMAE without GRN, which was stuck at 83.7%.
And then you have to use it all the time, right?
You do. They found that GRN must be used in both pre-training and fine-tuning. If you take it out during fine-tuning, the performance degrades immediately. It confirms that the new, healthy feature space the model has learned actually relies on this competition to function properly.
This brings us perfectly to Section 4, synergy and scaling performance. The key takeaway here, as we've been saying, is that these two parts are completely mutually dependent. GRN alone didn't dramatically boost the V1 supervised performance.
But FCMAE alone certainly didn't fix V1. It was stuck.
But the ConvNeXt V2 architecture plus the FCMAE framework provided this massive synergistic boost.
It really did. If you look at the V2 large model, pre-trained with FCMAE, it hit 85.8% accuracy. That's a huge 1.5% lead over its V1 counterpart that was just trained with supervision.
That one number proves that co-design was the missing link for ConvNeXt in this SSL regime.
And that success allowed them to do what everyone wants to do.
Right.
Scale the architecture across an entire family of models. This is huge news for industry because it means ConvNeXt can now provide solutions across the whole compute spectrum.
From the ultra-efficient 3.7 million parameter ADO model,
Which is perfect for mobile or edge deployment.
all the way up to the new, huge 659 million parameter model for massive cloud computing.
The fact that it scaled so successfully from ADO all the way to huge demonstrates the incredible robustness of the V2 design. It's really the first time the benefit of mask image modeling has been demonstrated across such a broad capacity range for convolutional networks.
So how did they stack up when they benchmarked these new V2 models against the state-of-the-art, specifically against FCMAE and Swin Transformer, which uses a variant called SIMIM?
The results were incredibly competitive. V2 consistently outperforms the Swin train models across all sizes.
And against the original champion, FCMAE.
There, V2 really holds its own. It often performs identically up to the large model size, but, and this is a big but, while requiring significantly fewer parameters.
Can you give an example of that?
Sure. The ConvNeXt V2 large model achieves basically the same performance as VT large, but with 198 million parameters versus VTL's 307 million.
Whoa! That's nearly a 35% reduction in the parameter count for equivalent performance.
It's a crucial efficiency win. Fewer parameters means a smaller memory footprint, it means faster inference, and often it means faster training.
But the true headline result, the one that made everyone sit up and take notice, came when they pushed ConvNeXt V2 into the extreme capacity regime using larger datasets.
That's right. They introduced a three-step training process that's now pretty standard for claiming state-of-the-art.
Walk us through that.
Okay, phase 1 is the FCMAE pre-training on ImageNet 1K that we've been talking about. Phase 2 is supervised fine-tuning, but on the much larger, more diverse ImageNet 22K dataset.
And phase 3 is the final step, a final supervised fine-tuning back on ImageNet 1K for the final benchmark number.
This methodology is common practice for squeezing out the maximum possible performance in these giant vision foundation models.
So, what was the final score for the ConvNeXt V2 huge model?
The ConvNeXt V2 huge model, after following this three-step process, achieved a new state-of-the-art accuracy of 88.9% top 1 accuracy on ImageNet 1K.
And again, using only publicly available data.
Yes, that is a loud and clear message to the entire field. It confirms that pure convolutional models, once they're properly modernized via this co-design philosophy, are not just competitive. They can actually set the high bar in the largest scale vision learning regime, directly challenging the previous dominance of the transformer family.
Okay, so that brings us to section 5, which focuses on what I think is the true measure of any foundation model, transferability.
Right. It's not enough to be good at ImageNet. We need to know if the features learned during that FCMAE pre-training can generalize well to complex downstream industry tasks like object detection and segmentation.
Let's start with object detection and instant segmentation on the CoSEO dataset. They use the established mask RCNN framework. So how did V2 stack up against its supervised V1 ancestor?
It was a clean sweep. The V2 FCMAE models consistently outperformed the V1 supervised models across all sizes. It's really strong evidence that the initialization provided by this co-designed self-supervised pre-training yields a far more robust set of transferable features than just training on ImageNet labels alone.
And what about compared to the transformer competition, specifically the SWIN transformer using SIMIM?
Again, V2 FCMAE proved superior across the board. The performance gap was actually most pronounced in the larger models, but even at the base size, the V2-based FCMAE achieved 52.9 AP box versus SWIN-based SIMIM's 52.3.
That suggests that the feature representations developed with FCMAE and GRN are just inherently more suitable for these dense prediction tasks, which really require high spatial fidelity and diverse feature maps.
That seems to be the case. Moving on to semantic segmentation, they tested V2 using the UberNet framework on the very challenging 80E20K dataset. This is a task that heavily relies on both high-resolution local detail and global context.
Meta results.
Here, V2 FCMAE performed on par with the SWIN transformer at the base and large model sizes. They were neck and neck. However, when the capacity scaled up to the huge model, ConvNeXt V2 significantly pulled ahead.
How far ahead?
The V2 huge FCMAE achieved 55.0 MIOU versus SWIN V2 huge SIMIM's 54.2 MIOU. That's a pretty significant gap at that level of performance.
Why do you think V2 pulls ahead specifically in the huge model regime for these transfer tasks? What's going on there?
I think it connects directly back to the GRN layer. The larger the model, the more parameters it has, and the greater the risk of that catastrophic feature redundancy we talked about, especially when you're training on sparse input.
So GRN's explicit role is to enforce diversity and channel competition.
Right. And as the model capacity increases, that corrective mechanism becomes absolutely vital for maintaining a rich feature space that's capable of transferring seamlessly to new domains like segmentation. The SWIN model, while it's very powerful, might not have such an explicit mechanism to fight redundancy during its MAE training.
And that could lead to a performance plateau at that extreme scale.
That's my hypothesis.
Yeah.
And the highest segmentation result they reported, a very impressive 57.0 MIUU, was achieved by the V2 huge model, using that intermediate ImageNet 22K fine-tuning. That robust transferability really confirms the successful modernization of the ConvNet.
Okay, now we absolutely have to return to the efficiency analysis because this is perhaps the single most important metric for any practical industrial adoption.
It really is. We talked about using sparse convolution during pre-training, but we need to quantify the real-world impact. What does it actually save you?
That sparse convolution was primarily introduced to prevent information leakage and achieve efficiency, but what did it actually deliver in the hardware benchmarks?
It delivered tangible, I would say, game-changing resource savings. Because the model was only processing the visible 40% of the input during that computationally heavy pre-training phase, they observed an average 1.3x increase in training throughput.
So the training just runs 30% faster.
And, critically, a 2x decrease in maximum memory usage compared to a dense masked convolution approach.
Okay, let's pause on that. A 2 times memory reduction. For any engineer or researcher out there trying to train large foundation models, memory usage is often the ultimate bottleneck.
It's everything. It dictates how many GPUs you need, the batch size you can use, how long the job takes, whether you can even run the job at all.
Exactly. Training these 650 million parameter huge models requires specialized high memory hardware.
And cutting that memory usage in half during the most expensive phase pre-training makes the development and iteration of large ConvNeXt feasible for a much wider range of institutions. It dramatically reduces the cost barrier to entry for training massive state-of-the-art vision models.
So that efficiency wasn't just a nice side effect.
No, it was a necessary component of the code design strategy that enabled the scaling in the first place. Without it, the huge model might not have even been practical to train.
Okay, so we've thoroughly analyzed the initial problem, the synergistic solution of FCMAE and GRN, the scaling success, and the impressive transferability. So let's try to tie this all together into our key takeaways for you, the listener. What does ConvNeXt V2 really mean for the future of computer vision?
First and foremost, ConvNeXt V2 is a definitive proof point. Pure ConvNeXts are not obsolete, not by a long shot. They have successfully bridged the gap and are now completely competitive in mask-based self-supervised learning, which was a domain that transformers seemed ready to just claim permanently.
And the paper meticulously argues, and I think the results really affirm, that co-design is the key. You cannot separate the FCMAE framework, that sparse-aware training method, from the architectural tweak, GRN, which manages the feature competition.
The V1 architecture just wasn't resilient enough. It couldn't handle the stress of masked input without this explicit mechanism forcing diversity.
We should also briefly mention the context against other self-supervised methods. They ran an extra experiment comparing FCMAE, their masked image modeling approach, with MoCo V3.
Right, which is a state-of-the-art contrastive learning method.
And what was the outcome there?
FCMAE yielded better representation quality. It got 84.9% versus 83.7% accuracy on the ImageNet 1K fine-tuning task.
So that finding really validates the global research trend that's been favoring masked image modeling over some of the older contrastive methods like MoCo for achieving that peak fine-tuning performance. It confirms V2 chose the right type of SSL challenge to optimize for.
Before we wrap up, let's circle all the way back to the feature analysis that underpins why this V2 design is so good at transfer learning. I'm talking about the analysis using the class selectivity index. This is a really important concept that speaks volumes about what makes a foundation model universally useful.
Okay, so the class selectivity index, it measures how tied a learned feature is to a specific class, right?
Exactly. If the index is 1, the feature is highly specific. Think of a filter that only activates for cat whiskers. If the index is 0, it's highly class agnostic. It activates for generic things like edges, gradients, or geometric shapes, regardless of what the image actually contains.
And they analyze the distribution of this index in the deeper layers of V1 versus V2 when both were trained with FCMAE.
Yes, and in the powerful V2 model, they found a more bimodal distribution. What that means is there were 2 distinct peaks in the distribution.
One peak, I assume, corresponds to the highly class-specific features, which you need for the final classification task.
Correct. But the second, often lower peak, suggests that V2 has successfully learned and, more importantly, maintained a larger population of more class-generic features than V1 ever could.
And that's the deep insight. Class-agnostic features are the very definition of transferability.
They are. If the feature maps aren't overly focused on just ImageNet labels, they're inherently more valuable when you pivot to entirely different tasks, like detecting objects on CodeKeo or segmenting complex scenes in AD20K. This bimodal feature distribution is a signature of robust foundation models.
So the GRN layer, by enforcing competition and fighting redundancy, it essentially forces the network to maintain this crucial reservoir of class-agnostic features.
It turns out that feature diversity, enforced through an architectural tweak like GRN, isn't just a nice-to-have. It's a necessary design principle for achieving maximum transferability and scalability in the self-supervised era.
Which leaves us with this final, and I think provocative, thought for you to explore. We now know that pure ConvNeXts can compete at the very highest level of vision modeling. But the success of ConvNeXt V2 was based on optimizing for both efficiency and, crucially, feature diversity through GRN. So, does the future of building highly scalable, effective, and easily transferable vision foundation models lie less in just maximizing raw classification accuracy and more in engineering systems through mechanisms like lateral inhibition and competitive normalization that explicitly encourage and protect these class agnostic feature representations during the self-supervised pre-training phase?
It's a great question. V2 suggests that the most powerful model might not be the one that's just the most accurate classifier, but the one that generates the most diverse and resilient set of basic visual primitives.